Hello, everyone, and welcome to today's webinar. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is Dennis Hinz. Dennis is a senior thermal and CFD engineer at Thermal Analytics, where he leads the development and validation of advanced cabin simulation methodologies. Dennis specializes in coupling 1D and 3D solvers with human thermal comfort modeling to create integrated multiphysics simulation workflows for cabin environments. Recognized for his meticulous approach and innovative problem solving, he delivers solutions that are both highly accurate and tailored to client-specific needs. Dennis holds a BSc in chemical engineering from the University of Michigan and a PhD from the Illinois Institute of Technology, where his research centered on CFD model development and validation for complex multi-phase flows. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We are also recording this webinar and we'll be sending you the link to the video following this presentation. And with that, Dennis, if you're ready, you may begin.
All right, thanks, Chris, for the introduction, and thanks everybody for joining. Welcome to the webinar. The title of today's webinar is Optimizing Defrost Performance Through Thermal Simulation. So we'll start out with an introduction to defrost simulation. We'll discuss the performance requirements imposed by physical testing protocols, and then I'll quickly touch on the motivation for using simulation for these types of evaluations. We'll look at a couple different workflows on the spectrum of simulation methods. First, a very high accuracy approach, that's the GT, TAITherm, and CFD coupling. Then we'll benchmark the GT, TAITherm rapid flow solution and demonstrate the capabilities for rapid design studies with this workflow. And finally, we'll conclude with a short Q&A. So defrost performance requirements are imposed by global regulation. In the US, this is in FMVSS, for the EU in ECE regulation number 43. And essentially what we're doing in these test procedures is we're segmenting the windshield into various regions or zones. You can see some images here on the left dictating how these regions should be defined. For the purposes of this webinar, we'll refer to region A or zone A as this part in front of the windshield, and then a larger region here covering most of the windshield as region B. You can see the performance criteria here in the table on the right. Basically, region A should be 80% melted in 20 minutes, and region B should be at least 95% melted by area in about 40 minutes. In the physical test procedure, you can see some images here below. You can see the test engineer in the cabin drawing some defrost patterns on the inside of the windshield as they progress over time. And then they're using these markings to calculate the percent area melted. So we'll show in this webinar how we can extract this information using TAITherm. The important thing here is that we have some strict performance criteria that we have to meet, and those criteria are applying some constraints on the design process. And what's the role of simulation? Well, the automotive industry is increasingly adopting virtual verification and validation techniques to reduce development time and cost, but also to enhance the design process. You can see that here on the left manifesting in the continued growth of the automotive simulation market over the last decade. There's many benefits to involving simulation in the development process. There's reduced development time. So for the defrost application, we can evaluate, for example, different windshield or HVAC designs early on in the process. We can find issues and save time and money required down the road during physical testing. We can also add value using simulation by gaining some insights into complex physics. For defrost, we can look at windshield glazing, different windshield types, exploring different HVAC system components when they're integrated. And depending on where you are at in the development process, you might have some different requirements and constraints in terms of accuracy and lead time. So later in the process, over here on the right, you may be more interested in obtaining a very accurate solution, and that may be a bit more time consuming. So we'll look at one such workflow in this webinar. That's three-tool coupling, which is the coupling between GT Suite, TAITherm, and a CFD tool. It can really be any of the large commercial CFD tools. Earlier in the development process, we may be more interested in a workflow on the other side of the spectrum, much lower lead time, but possibly trading a bit of accuracy to get that bump in computational speed. So in this webinar, we'll explore that trade-off with the GT TAITherm rapid flow coupling method. So those are the two methods we'll focus on in this webinar. The first one we'll look at is the fully transient three-tool coupling method between GT Suite, TAITherm, and CFD. In this webinar, again, we're using star CCM. So the HVAC system model provides accurate model of the HVAC control system, the vent flow rates, the temperatures, and it provides these transient inputs to the CFD model. The CFD model then solves the fluid flow field over time and exchanges convection and thermal boundary conditions with a thermal model in TAITherm. And that data exchange between thermal and CFD solvers is what facilitates the cabin conjugate heat transfer solution. So most importantly, for defrost, the thermal model allows ice to be deposited on the windshield. It's characterizing the thermal properties of the windshield, and then it's predicting the melting process. Now, the 3-tool coupling workflow, it's been pretty well validated for the cabin. It's been shown to achieve accuracy within about 2 or 3 degrees. So with this method, we can be sure we're getting accurate local air and glass temperature predictions, and also accurate prediction of the ice melting process. This is an image of the HVAC system model used in this webinar. We have a refrigerant loop, a heater, and this is a warm-up scenario, so the heater is active. We have some HVAC system ductwork that's predicting the flow rates and the temperatures at the vents. This is a defrost scenario, so we have 100% fresh intake. We're in defrost mode, and we're operating at max blower speed. So as I mentioned, the CFD solution is performed in star CCM. The most critical thing here with the CFD model setup is that we're receiving transient vent boundary conditions from GT. You can see some of the GT setup of the ductwork and vents here on the left, and we're passing this information to the CCM model. And these are transient boundary conditions that we're passing. Our co-simulation tool, TAITherm, is handling this data exchange. There's features in TAITherm that allow easy adjustment of the CFD boundary conditions, either as parameters or field functions. You can see this variable assignment happening here. On the TAITherm model side, it's a pretty standard setup in terms of the material property definition and the vehicle setup, but there are a few important things to point out regarding defrost. Our windshield and optionally other windows have the moisture transport model enabled. So this is what enables the phase change solution on the glass. In the initial conditions, we can specify the initial ice concentration, and this is coming directly from the test procedures. We've parted out the windshield into the different regions. So this is so we can extract percent melted data from our regions of interest on the windshield. And then there's a couple user routines that we can enable to enable some of these post-processing features. The ice thickness calculation, so we can get contours of ice thickness, and also the percent area melted calculation. So for this, we do need to define some parts of interest that we want these user routines to operate on. So just a list of the parts here on the windshield. Some other useful boundary conditions down below for this simulation. Ambient temperature, very cold, -18°C, pretty low wind speed in the test chamber, and a duration of 40 minutes. So on this slide, we're looking at the defrost patterns coming from the 3-tool coupling simulations. And there's a couple ways we can visualize the defrost pattern from TAITherm, and that's what we see here. One way on the left, another way on the right. So the first way on the left is to just look at the temperature distribution in the TAITherm GUI. And this is the animation we have here on the left. As we know, if the windshield external temperature is below 0, the ice we put there initially is still present. It hasn't begun melting yet. The windshield warms up over time, and when we reach 0 degrees, it begins to melt. And not until all the ice is melted do we see temperatures increase past 0. So basically what we're seeing is a contour. Everything, any other color than white means the ice is completely melted, and white is any temperature less than or equal to 0, meaning ice is still present. The other way is to hook the user routine for ice thickness, like I've shown on the previous slide. So on the right, we're seeing a contour of the ice thickness progressing over time. So this will calculate local ice thickness and output an Insight case file with transient data. This Insight case file can be viewed in your post-processor of choice, like ParaView, for example. On the right, this is actually a contour of the local ice thickness. So black means ice is 100% melted. Any other color means ice is still present. The other key post-processing metric to quantify performance is the percent area melted in each of our defined regions and zones. Percent melted for zone A is plotted on the left versus the target of 80% melted in 20 minutes. Zone B plotted on the right versus the target of 95% melted in 40 minutes. So you can see we're not quite meeting our performance target, and we'll address that later on when we look at some different case studies. But the important thing here is that we can easily calculate the percent melted within TAITherm. We just need to hook that user routine like I showed, and TAITherm will output a file that can be opened in Excel. So I just showed the result from our highest accuracy method. You saw that we're not really meeting our design targets. So in this hypothetical development scenario, it might have been useful to have earlier in the development process a simulation workflow that could be executed quickly and could be used to do some design studies, identify some of these issues earlier on. So in this next portion of the webinar, we'll shift focus to the GT TAITherm rapid flow coupled solution. We're going to benchmark that solution against the high fidelity approach and kind of investigate that trade-off in detail. So rapid flow, if you're unaware, is a transient flow solver completely integrated into TAITherm. It was released officially last year with TAITherm 2024.2. It's not necessarily meant as a direct replacement to CFD, but rather as a complementary tool to enable fast transient thermal simulations. Rapid flow is a Navier-Stokes-based solver, but it does have some simplifying assumptions to increase speed. The major ones are InVisid and empirical modeling of the boundary layer thermal effects. So these assumptions allow rapid flow to run on a coarser grid. You can see the grid up here. It's a 20 millimeter Cartesian hex grid, and also with larger time steps. In this workflow, you can see here above, we're coupling GT and TAITherm or rapid flow, both where TAITherm and rapid flow are both integrated within TAITherm. Basically, the GT HVAC model is supplying the transient vent boundary conditions to TAITherm. You can see the simulation speed comparison here in the table. The 3-tool coupling method, when run on hundreds of cores, will take something like a week. It depends on your specific cluster. While the rapid flow solution took only a few hours, right? The bottleneck here for this 3-tool coupling is CFD, right? So running 40 minutes of CFD in real time can really take some time. Of course, there are some simplifying assumptions, like I mentioned. So the speed up is nice, but we do also have to compare the results here in detail shortly. You could see some initial velocity contours here. One is from ParaView, one's from Star CCM. So the scale's not exactly apples to apples, but you could see, similar flow field behavior. Before I do that accuracy comparison, first a few notes on how we can set up this coupling. If you're familiar with the standard GT TAITherm cabin co-simulation, we're using that same thermal mesh co-sim template to facilitate the coupling. Basically, we just need to point to a thermal model and define a coupling interval. On the TAITherm side, to initialize the rapid flow solution in the cabin, we just need to create a fluid node. You can see that here. We select the checkbox to enable rapid flow for this fluid node. By the way, this is a new feature in 2025.1 if you haven't seen it yet. And then we link all of our bounding surfaces, the bounding surfaces of the flow solution via library convection to that fluid node. Okay, having done all that, TAITherm will know, okay, this means we have rapid flow convection for the cabin interior. It'll mesh the cabin and it will run automatically along with the thermal solve. TAITherm model signals in the thermal mesh COSIM template are used to send data from GT Suite to TAITherm. You can see we're sending defrost inside vent air temperatures over time here in this image. These are transient inputs in this case. On the TAITherm side, we're receiving those as input parameters, which update the rapid flow boundary conditions. So those are defined here in the config file. You can see, for example, defrost set to an input parameter in this little snippet we have below. This slide shows a comparison of the percent melted results from the 3-tool coupling simulation in black compared to the GT TAITherm rapid flow solution which is the blue line. Zone A plotted on the left, zone B on the right. You can see there's some slight discrepancies, but overall fairly good agreement given the trade-off in computational time. Here on the left, we see a comparison of the windshield interior surface temperature. Again, three-tool coupling is in black, and then the GT TAITherm rapid flow solution is in blue. The solid line in the middle is the windshield average temperature. You can see that compares extremely closely. We do see some larger discrepancies here on min and max temperatures. Those are the dotted lines. So maybe the air distribution isn't exactly the same, but on average we're getting pretty close. On the right is the comparison of the average head level temperature, average of the 4 temperature probes you can see in the image above. Again, we see a slight difference, but pretty good given the simulation time trade-off. Finally, showing here a comparison of the ice thickness contours over time, 3-tool coupling on the right, the GT TAITherm rapid flow solution on the left. And the story here is similar to what we just saw on that windshield temperature plot. On average, and in the primary defrost region, the agreement's pretty good. The bigger differences are in the airflow distribution further away from that primary defrost region. Again, here in this contour, black means 100% melted, and any other color means ice is still present. So in summary, we have a case here. We're not quite meeting our required performance criteria of 80% melted in 20 minutes. We've also demonstrated a simulation workflow that runs pretty quickly that we can use to compare designs. So another goal of this webinar is to highlight the capabilities of the simulation workflow, GT TAITherm rapid flow, to perform rapid design studies. So there's a few things we can look to adjust right away. We can look at the glazing, which refers to the structure and makeup of the glass, composition, layers, coatings, thickness, etc. We could look at the HVAC sizing. So the glass basically isn't warm enough, especially in the zone A region. So we could upsize the blower or the heating capacity. Since we have the GT HVAC model integrated, we can reliably modify or switch out any of those components. We can look at active heating techniques, embedded resistive wires, conductive transparent films. We can explore that trade-off between energy efficiency over time and that original cost of this technology. We can also adjust the HVAC ductwork and vents to alter the air distribution pattern. So we'll look at the effects of a few of these in some quick case studies. So here's the first result. I'm comparing the conventional automotive glass, which is the black line here, to a few different modifications. In purple, that's a low emissivity coating applied to the interior surface. So in theory, we're reducing the energy lost from the glass to the cabin by decreasing the emissivity, decreasing the radiation losses. A little bit surprisingly, it showed little to no effect in this case. Might even be slightly worse in some cases towards the tail end of the defrost. I think the dashboard's also getting quite hot, so in some cases we're actually receiving radiation heat to the windshield. The blue case is adjustment of the glass thickness to 75%, so just increasing the rate of conduction through the windshield. Of course, there's other design considerations, structural and noise considerations that would need to be considered, but here we're just focused on the thermal solution. The orange line, in terms of result, was quite similar to the glass thickness case. In this case, we've upsized the blower by 25% and also the heating capacity to match. And finally, in green, this is 50% upsized blower and heating capacity, also with 75% glass thickness. And you can see in this case, we're actually finally close to meeting our performance criteria. So the important here to point out, with this workflow, we can go through a lot of these cases quickly, and we have the ability to modify a lot of our key inputs. Now, the other key input where TAITherm adds a lot of value is in the glass modeling capabilities. So if we know the thermal and optical properties of each layer within the glass, we have the ability to define a multi-layer transparent part in TAITherm. So for defrost, we can use TAITherm to predict thermal differences between various glass types and the effect it has on defrost. So we'll look at one more case, and this final case we're interested in is the application of a conductive transparent film to be used as an applied heating device. So ITO, indium tin oxide, is a transparent conducting material, so it can act as a resistive heater distributed over the interior surface of the windshield. You can see that in the image below. In this windshield, the bus bars distribute current across the film, applying a heat rate to the interior layer of the windshield. So on the right, plotted in pink, is this ITO coating applied on the interior with 15 watts of heating power. And you can see even with just 15 watts, this actually outperforms the previous best case that had 50% upsized blower and heating capacity. So if we look at this plot below, this is the heat rate, from those cases, the previous base cases. And if we just think 50% of that, that's about 3 to 4 kilowatts of additional power applied by the HVAC system, to obtain that difference, right? And that result is similar to just 15 watts applied directly to the interior of the windshield. So we can already see, this is a pretty promising technology, especially for EVs, where energy savings during operation is more critical. Also, as these technologies become more cost effective and make it to the market. So in conclusion, we showed that coupled GT TAITherm flow solutions can be used to obtain accurate predictions of vehicle defrost performance. We showed some high fidelity solutions for validation for high accuracy results. We also showed the trade-off of the GT TAITherm rapid flow solution. It's a favorable trade-off between accuracy and computational time, which enables some rapid design studies. We showed that TAITherm provides a variety of visualization and reporting features. So we can look at defrost patterns, we can look at the ice thickness over time, and we can calculate the percent area melted for our zones of interest to match the test specifications. And finally, TAITherm enables some detailed characterization of windshield thermal and optical properties. So in this webinar, I showed the latest and greatest for defrost, but there are some things still on the horizon. A big one here is rapid flow local mesh refinement, which is planned for 2025.2. So this enables resolving the HVAC ductwork and vents efficiently for the evaluation of the airflow distribution. There's also some notes coming about moisture transport in the air. This is probably more relevant for demist, defog, but this is planned implementation in 2026. And I'll also mention the standard GT TAITherm co-simulation, the feature to integrate the moisture transport model on surfaces and the interaction with the moisture in the air in the flow solution is coming soon as well. I'll flash the references quickly, and then I think we can open it up for Q&A. Thanks everybody for attending.
Yeah, thanks, Dennis. All right, so first question, can the features shown like percent melted also be applied to other transient workflows?
Yeah, that's a good question. So I showed the spectrum, and I only showed a couple methods there. There's a lot of different ways. We can do this conjugate heat transfer coupling and integration with 1D system tools. Yeah, these percent melted user routines or ice thickness, it can be incorporated in any other workflow you have.
All right, thank you. Can you also do defog or demist simulation like this?
Yeah, so for that one, as I mentioned in our coming soon slide, probably the best, yeah, I'll flash back to that one. Yeah, the best one's probably the GT TAITherm co-simulation workflow for that one, just because moisture transport interaction with surfaces and moisture in the air is enabled there. For the CFD approaches, we can do some 1D, kind of moisture balance inside the cabin to also integrate it in those cases, but that would be a simplified version versus the local humidity in the air that you might get from this approach. And then it's also coming in rapid flow in 2026.
All right, thank you. You mentioned local mesh refinement coming in the future. How will that benefit the workflow?
Yeah, so if you remember the image of the grid, it was a uniform Cartesian grid. So if we want to do things like, increase the refinement near the windshield, or if we want to get, the exact representation of the airflow distribution coming out of the vent and the interaction with the louvers and things like that, we can't really right now efficiently mesh that with a Cartesian uniform mesh, right? So this local mesh refinement really will enable those types of things, right? Local refinement where needed, like on the windshield, and then actually capturing the airflow distribution through the ductwork and into the cabin, which I know is so important for many of our customers. So yeah, definitely looking forward to that.
All right, well, looks like that'll do it for questions. So that will complete today's webinar. We appreciate you all attending. You will receive a follow-up email this afternoon containing a link to to watch the recorded webinar session. Again, thank you, Dennis, and thank you all. Everyone have a nice day.